Good morning, everybody. Today we have a Codeforces Div 3 round, but before that we have some announcements. So, first of all, I'm back. It was a great vacation. If you were wondering where I was at ICPC World Finals, so I have some cool things to show off. We got this mouse pad here, all this other stuff. This guy named David, not me, different David, gave me this awesome candy. Apparently it's like coffee flavored, so it's really good. Very much recommend it. If you're not interested in the announcement, you can skip to like 3 minutes into the video. That's when the contest starts. But otherwise, hopefully you are. I mean, why not? It's cool new stuff. So, first of all, I just want to say thank you guys so much for just being terrific people. There's all of this stigma about YouTube comments and how it's really just nasty and mean and stuff. But honestly, like, so much of the feedback I get is just very positive, helpful, encouraging stuff. And that's great. But once in a while, something will come up, and especially it'll be something that, like, where you know it's true. And that's the reason that you notice it. And the recent example of something that's happened recently is this guy who's a Cyan, SSVB. He was looking for an example of someone taking a contest very seriously and trying very hard in it. And one of the things he said, which I really noticed, was, as for second thread screencast, it looks more like an artificial spectacle than real participation. I suspect he could have done better if he focused more on the contest and didn't have to provide commentary. And I thought this was, really insightful because, a big part of it was, yeah, that's probably true. So I decided that for this round, I'm not going to do this for every round, but for this round, I'm going to go less on the commentary and more super try-hard pants. And that's what we're going to do for this Div 3. We're going to do is focus as much as possible on just performing well in the contest. And we'll see how we do. After the contest, I'll focus more on commentary, and I'll talk about the solutions to all of the problems. I'll probably go over like maybe A, B, and C pretty quickly because they should be pretty easy to understand concepts. And then I'll talk about the harder ones, if there are any harder ones this contest. I guess we'll see. It's Div 3, so it should be somewhat easy. But I'll talk about those afterwards. Other than that, there's a lot of cool stuff in the works, so I guess stay tuned. We'll have some cool shorter videos coming up soon. Not full commentaries here, but it should be fun. I guess since we are talking about try hard things, usually before contests, if they're super early in the morning, I try and do like some sort of exercise beforehand. A good one that I'd recommend is just push-ups. They're very easy to wake up, get focused for, if you would otherwise be tired, because it's still kind of dark out here in Seattle. All right, 10 seconds, here we go. We got Codeforces all set up. I'm gonna keep it a little bit smaller, and then the video quality will improve later on. Initially when I upload it, it's not great, but it'll improve later on. All right, here we go. Yeah, so you shoot the max and then see whether that is you. Okay. this should be good. Yeah, that's fine. Oh no, we got this one wrong. Okay. Yeah, why did we get this wrong? So, sorted. Okay. Got it. Nice. Select any digit and remove it. Okay. Divisible by 27, divided by 25, and positive. So what numbers are divisible by 25? If it ends in 0, 0, or 2, 5, or 5, 0, or 7, 5. Answer exists. Only 3. Yeah, okay. Loading zeros. Nice. 2. So the length is 2, I is 0, yeah. On to C. There's 1 cat, K mice, and 1 hole on a coordinate line. Okay, got it. Cat's at point 0, the hole's at point N. All mice are located between the cat and the hole. Ith mouse is at point X, I. You're gonna have many mice at the same point. Exactly 1 mouse moves to the right by 1. Yeah, okay. Maximum number of mice you can save. Does the cat start at 0? Yeah. So you can do greedy, so sort it, keep the rightmost, and then probably just keep going until you run out of time. Yeah, I think that works. think this is sufficient. It's not. I say we can save 2, we can only save 1. Two. So why is that? You have 2 things here. Because you really have, so this is just time minus 1. This is how much time you actually have. Okay. Yeah, let's submit this. Wait, they say. Okay, that's fine. I think we're fine there, but I guess we'll see. Just a few seconds here. So yeah, here, D1 and D2 probably aren't too important to separate. We have an array, an even array of of positive integers. What? Oh, we have an array and also an integer. We perform the following operation of the array: take an index and reduce AI by k. All the numbers in the array became the same. Find the maximum k at which this is possible. Okay, so if they're all the same, the answer is -1. Otherwise, we need GCD of all differences to the first element, to the smallest element. Oh, they can be negative. So it can be arbitrarily large if they're all the same. Otherwise, you need the GCD to the smallest. Yeah. Okay. That sounds sketchy. Yeah, you just make everything the smallest. Why would that not be the case? N is scarily small. I think this is right though. Yeah, it's maybe it has to do with the fact there's a D2. This is a very concerning bound, but okay, anyway, let's just go for it. Okay. this. I think it's right. Okay, 15th place, not bad. Alright. Whoa, this is wacky. I got this new plugin, which is Caret, I think. I don't know what's going on here. Pi, delta just now, and whatever this is. Okay. Let's read D2, I guess, and then read E. It's more complicated. Half of same. Oh, okay. After that, Polycart began the following operation of the array. Take some index and reduce AI by K. Turned out that at least half of the numbers in the array became the same. Find the maximum K at which such a situation is possible. Oh, you just need at least half of them to be the same. Can you brute force which ones there are? Maybe. I don't know. Not easily. But n is quite small. Values are also kind of small. So we can make the minimum 0, but we might be able to ignore it. Can we use some sort of DP? I don't know. Let's think about that after we get E, maybe. Alright, we have a tree. Non-rooted tree. Okay. Removes all leaves of the tree. Okay. So you just need to know your distance to an edge, right? Your distance to a leaf is when you'll get removed. Yeah, if you are a leaf, this is 0. If you're adjacent to a leaf by 1, then you get removed on turn 1. Okay. And then you need the counting sort and then prefix sum. Okay, it's easy. Okay, so we have this, and then is K? Oh, we're given K. Oh. Did it have 14 nodes initially? Yeah, interesting. Okay, wrong answer, just 2. Yeah, this shouldn't take more than n turns. Nothing will have distance more than n. We can't have a sum of things more than n, surely. This is not the right answer. Ah, yeah, you don't become a leaf in that. Yeah, it's not a BFS, it's a top sort. Okay, let's break this, I guess. So yeah. 1, 2, 3, 4, 5, 6. 6 nodes, take 2 steps. So we say 0, the answer is 1. There should be just the 2 left over. Okay. So okay. Yeah, distance equals 0. That's some case. Alright. We've got safe notifications, so we don't have to wait. Alright, so we've got this, and we have this of solves. So G, changing brackets. A sequence of round and square brackets is given. We need to change the sequence by performing the following operations. Change the direction of a bracket from opening to closing or vice versa without changing the form. Change a square to round, having the same direction. Okay, gotcha. We have a string. Okay, we got it. Got E. So yeah, so we have D2G and then this one problem F, which we haven't read yet. We also haven't really finished reading G. So we have a string S of length N and Q queries of the type LR. For every substring S from L to R, find the minimum cost needed to make it a correct bracket sequence. Okay, this all has even length, so it's possible somehow. Yeah. The length. Wait, what? Sum of lengths. Yeah, so, oh, okay, so the number of queries isn't that big, but the array can be rather big. So we need some intelligence here. Not obvious. Not immediately obvious. How about D2? I guess D2 is the way to go. So we need at least half of the numbers to become the same. So it is not binary searchable. But K will be, K is either infinite or most 10 to the 6. Can we do 40 times 10 to the 6? Yeah, we just care about the thing, the values mod. So let's say we know what K is. K is less than or equal to 2 times 10 to the 6. Maybe 4 times 10 to the 6 to be safe. Can we detect when the answer is -1? It's -1 if we have at least half of the things the same. So yeah, so we have 2 times 10 to the 6. And then for each of these times 40 will be our runtime. So runtime will be 8 times 10 to the 7. It's gotten it close for 1 second. But it should still probably be fine. At least it'll be fine in C++. And then we just care about what values mod K exist. We just need to see if there's something that's a majority. Yeah, there's an easy way of doing that. There's some guy's thing. I forget what it is. Some guy's theorem. Okay. So we have this. Oh wait, is this? Oh boy. It's gonna get real close here. It's gonna get real close. We'll try it. I would really like a 1.5 second time limit here, though. I don't see any reason to make this 1 second. Test case is 10. Okay, CS at 8i. And then we have sysout max in CS times 2 is greater than n. And sysout minus 1. Continue. Alright, otherwise we need the majority. So for int k equals 0, k 0. No. This will be one pass through to get the max. Then we need the count of what it is. Yeah, it'll be 2 passes through. We can try it. Yeah, you might. So I think you just have to go through the array a second time. Oh, it's my Tealy. Not 13. Why not 13? Why not 2? Oh, we don't. Do we? What do we need? Yeah, what's wrong with this? best answer equals I mod k. There are no four things that are the same. Two minus one twice. Okay. I think we're fine here. But I guess we'll see. Okay, so cool. G's next easiest probably. Let's check standings to sanity check that. Make sure. Oh, maybe not. I guess not. Could be geothermal and a bunch of people following. Unclear. Let's check it out. Alright, red black number. We have a non-negative integer x, the decimal representation of which contains n digits. Color each digit red or black so that the number formed by the red digits is divisible by a. The number formed by the black digits is divisible by b. How big are a and b? Each up to 40. Oh, dude. As fast as in C++? Surely. Surely. Is this what's killing me? Test cases, 40 integers, each up to 10 to the 6. So 2 times 10 to the 6 loop times 40. Probably don't need to try every K. probably only need multiples of, or factors of some pair. Yeah, there's going to be some pair. What if there's 0? Well, then it won't matter. Yeah, so there's going to be some pair with some difference. How many difference do you have? 40 squared. Do we need all factors of that? Yeah. It's annoying. Okay, we can fix this, I guess. This is dumb. I think this would pass in C++, but I guess we'll see. Probably not that many. Okay. So now cube root of 10 to the 6. That's cube root of 10 to the 6 is 100. Yeah, so we're fine. Factors of the difference. Okay, this should be correct, hopefully. Yeah, runtime should be probably much faster, I think. Oops. Yeah, I'm not sure if the other one would have passed, I guess. It should have. They should have made the bounds less ambiguous. Just make it like 10 to the 8th if you don't want that to pass. Like, I don't know what they were doing with that. Wrong answer. Darn it. So is that true? Is it going to be some factor of the difference? Getting the factors right. Seems legit. Okay, so it's the GCD of some things. Yeah, it's going to be the GCD of some differences, right? We pick, so in the previous array, you pick some subarray. It's the GCD of all the differences. So if you have some number, you GCD it with some other number, you get a factor. So another word for greatest common denominator is greatest common factor, GCF, I think. So this should be true. is this no longer right? Oh, is this overflowing? Does this overflow? It shouldn't. If the difference is 2 times 10 to the 6th, we'll pass it before we get here. Test 2. One, two, three, four. Yep. Okay. What about? I don't know. Does it seem right? It's wrong, you say. Okay, well, we can come back to that in a bit, I guess. Oh, but it's by far the easiest problem. Why? Can this be wrong? I guess we had no guarantee it was right before. So they said if k can be arbitrarily large. Yeah, that just means half of the things are the same. If you don't have half the things that are the same, you can't do it an arbitrary number of times. So max in CS, so this is 0. What can I do? Should be fine. Okay, yeah, let's come back to this, because we might have to write a brute forcer and that'll take a while. Okay, so we have this, and then we have F. So red, black number, this is a digit descent DP. We have N, what is N? The number of digits? Yeah. Okay, we have N digits. We need to color them red or black. We need the red number associated by A, black number associated by B. Or -1 if it's impossible. Yeah. So these are all small, so we have a digit descent DP. So we have good classic DP. We have DP at which digit we're on. The A remainder. And the B remainder. And then our transition is either add to A or add to B. This DP will store whether it's possible. Do we also need whether each has leading zeros? May contain leading zeros. Okay, good. Yeah, so the leading zero part is convenient. Oh, no, never mind. Okay, among all possible colorings, we need to output any such value such that, what is this? R minus B. Consider the count of digits that are red and the count of digits that are black. We need to output any such value such that this is minimum. Okay, so yeah, so then we also need like another state here, which is like the number of red. Yeah. So if we know how many red we're gonna have, this is what, 40 cubed? Or 40 to the fourth? It should be small enough for us, even in Java, and not a 1 second time limit. Okay, let's write up the DP real quick. Okay, so what do we need here? We need a int n, int a. Guess we'll just use their variable names because they're pretty understandable. And then we need the line. Let's read an input first because it's easy. Okay, so we have this, should be fine. What now? Now we need to make our DP. We need to build back too, this is gross. Okay, at least it's easy. So n plus 1 by a plus 1 by b plus 1 by n plus 1. We have to so this will return whether or not it's possible. Yeah, okay. Cool. So if digit is equal to n, return n reds to pick equals 0. It does 1, otherwise 0. If n reds to pick is less than 0, then return 0 for impossible. If dp at digit r rem e rem n reds to pick is less than 0, or is not equal to -1. Then just return that. We'll return this at the end anyway. Okay, so we have this. We need to try the 2 ways of placing here, I think. Right? Yeah. Oh, we have some other stuff here. So if rrem is not equal to 0, yeah, then return 0. Brem is not equal to 0, return 0. If n reds to pick is not equal to 0, return 0. Okay. Cool. So then we have to brute force how to do this, and then we're given impossible examples. Good. Okay. So int place will be line at digit -0. be place in red. Works equals math.max, it works, and go of digit plus 1, rem times 10 plus to place, modulo r, modulo a. brem stays the same, and then nreds to pick minus 1. Okay. Otherwise, we can do the same thing, but in blue or black. So, yeah, these kind of just switched places here. So this is just a rem, and this is b rem, or I guess red rem, black rem times 10 plus to place, modulo b. And this is still same number to pick. Okay, as possible. Cool. All right, so now we have to, so this should be good now, I think. Yeah, so now you have to try all possible answers. So for int leave with equals 0, leave with is less than or equal to n. Just B for debug, and then we have to write the build back after. Okay, so boolean possible equals go of the digit 0, rm0, blue rem 0. This will be leave with. This equals 1. So if not possible, then continue. What are they saying here? We want to minimize minus b. Do they each have to be not empty? Okay, so this is 1 less than n. Yeah, so 2 is the best we can get, and then 4 is the best you can get. 1, 2, 3, 4, okay. And then 1, okay. Looks good. This is sketchy though. Because when this was 0 to n, we were getting some very odd answers. Oh no, that's still right, okay. So we just need the build back now. Good. Write the build back. Void build back. Okay, so if this is 1, then sys out r, and build back with this. So this should be fine. So then we just need to say if best is greater than n, this out -1, continue. Otherwise, build back 0, 0, 0, best, and then this out. And we should be good. This sounds not right, but we can try it. So that's right. I guess we might as well just submit, right? If I pass, I'm gonna submit anyway. Okay, then we'll see whether it's right or not. I guess we should just check while we're waiting. Okay, so what's going on here? This, I guess, well, I don't know, maybe it works. So mod 3, mod 13, that is not a multiple of 13. Oh, 65 is, wait, so 21 mod 3 works. What about 65? Mod 13? Oh, it does work. Okay. Alright, we got it. Don't need to check. Who are we? We could be wrong. Alright, changing brackets. Do it is just for kicks. Yeah, we do it just for kicks. Okay. So I don't know what's up with D2, but we'll have to write a brute forcer, I guess, in a minute to figure out our bug. Let's try this one. For practice, I guess. So we can change the sequence by, yeah, we can change some of these things. So n is very long. This is actually a good problem. I like it. I don't have a very clear idea of how to handle it. What about just like the greedy case? So if two things don't match, all that matters is how much they don't match by. Yeah, Yeah, so things either don't match by one category or by two categories. You have to pay one for each of the ways they don't match. But you also have the direction. Oh wait, no. Well, yeah, it doesn't matter whether they. It's just like the categories, all that matters. So you also have to pay for the direction. I have to go to the bathroom. All right, so one observation is that if we have all brackets of one type, the only change we would make, like obviously we'd only change direction because it's helpful to not have a diversity of brackets. Having everything being homogeneous is very useful, makes things easy. But the only change we would make, okay. You might have too many of one kind. Well, if you have too many closing, you change the prefix of the opening. So you change like a prefix of the closing into openings, and then you need like a suffix of openings. And those go to closings. So you can do both of those with like range minima. All right. So we have those. You can't necessarily say if these things work separately, they work because of this example here. So we can't just split up the queries because they're not independent. So how do we handle it? Yeah, so I guess what, like, does the stuff that we flip, like, suppose we have too many closing brackets here, does it matter which ones we make become open brackets? Oh, I don't know. Does it? Like, we have two different closing brackets and then two more closing brackets. Well, that wouldn't be a good example. So we have an opening bracket, a closing bracket, and then another closing bracket, and then a third closing bracket. So we have to change one of the middle two. So if they both match, it doesn't matter. What if one of them matches? Well, if they're both the same, it doesn't matter. What if they're different? Is it always the second one? So in this case, it would be, we want the second one, but what if it's this other case? I guess this. Well, either we pay 3 to do this, or we pay 1, 2, 3. So I guess it doesn't matter. So always make it the rightmost one. Yeah, so I guess if you hit 0, you're going to get flipped. Okay. Yeah. Is that always true? I think I just proved it, right? Yeah, if they're the same, otherwise they're different. So yeah, you might as well. Like you're gonna have to change both. You can either change both, or you can change the orientation of the first one, and the type of the second one, and then the type of something earlier, because they don't match. Yeah, I think. Okay, what if these are both like this, though? Well, that's the same as the first case. No, I guess I haven't tried this case yet. Oh, maybe this does matter. So it would cost switch. Oh no, it would just be the same. Yeah, okay. So anytime it goes negative, if the prefix sum goes negative, then we pay for half of it. Then we pay 1. Otherwise, we need the things that mismatch. So, okay, yeah, so now we just have like, well, does the order matter? Can we just like swap every other or something? Yeah, every even index will match with an odd index. But which odd index? Seems a bit excessive for Mo's. Yeah, definitely too hard for Mo's. Man, I'm going through a lot of paper for this div 3 problem. Holy cow, dude. Ooh, okay. Yeah, how do we determine the cost of changing the types? I mean, the other part we can just do with a segment tree min query or something. We should do like the min prefix sum. If the min prefix sum is like -4, then we pay for 2 of them to be positive, and then we need to make 2 closing things. Closing. Which we would do at the end. Ugh. Yeah, I guess just the last 2. a cost can always be very large. It can always be arbitrarily large. So it's not something silly like just notice it's always going to be 1 or 2. Okay, yeah, I guess let's just say what if we did it for a single string, not worry about the query part. So we have some like stack. Of types, like this. Yeah, stack of openings. Every time we hit a closing, we add one if it disagrees. Or if the stack is empty, we insert it instead. And then at the end, we have to fix half of them. Oh, but that's like annoying. So what if we can have this. Or we can have open, 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 open. Yeah, it's like non-trivial at the end too. Oh, I guess it doesn't matter? It does though. We need an even number of each type. But if we do have an even number of each type, it still isn't necessarily possible. Man, this is hard. How are people getting this so quick? Yeah, lots of solves. Okay, let's go back to D2. I guess writer brute forcer, figure out what's wrong. Guess 52. Okay, so for this brute force answer, what do we need to do here? Oh, okay, so find some subset. Okay. Otherwise, there's some answer. Let me make sure we have over half of them, and then go through each bit, and then okay, so array small equals new int array and bits. Okay, then we go through so if mask and 2 to the I is not equal to 0. And this equals 8i. 5, huh? How is the BS answer 5? There isn't even a pair with difference 5. 5? What? 5? How do you get 5? There's no way it's 5. 5 and what? If it's solve. Oh. Two BFF's answer is 4. Okay, well, I guess this is a legit thing. The answer is in fact not 2, it's at least 4. We do try 4. Count is 1. Best answer is 3. What the heck? 1, 1. I guess this only finds a majority. That's annoying. It doesn't necessarily find a tie. examples were broken. That's kind of wacky. Okay, D2 should finally be good to go. Yeah, that's good to know. Anyway, all right. I wonder, are these TLEs? They are. Okay, that's fair. So maybe we weren't totally Java on it. Let's get G real quick here while we've got some time. Oh, how do you do G? What the heck? This guy, stop it. Will you go away? Obnoxious. See, that's an example of like just like random nonsense that just totally ignorable. Nobody cares. Like chaotic nonsense. Okay. How do you solve this problem? So wait, my hypothesis is that if we have a bunch of close ones, it doesn't matter. Well, we have to do the first one, right? So this has to be an open. And now after that, I'm saying it doesn't matter which ones you do. It might though. So you can imagine like this or like, yeah, so that's just not true. So which ones you turn around matters. But once you know which ones will be, like once you have the order, I guess once you have the order, it's easy. Yeah, once you know the direction everything is facing, then it's just the number of mismatches. So it's like direct things in such a way that it minimizes mismatches. Doing that is harder than it sounds. I guess at each step we have a choice, right? We can either go left or right. If we go left, we know who we match with. The only other choice is to go right. If we have someone we can match with, we might as well. But if you don't have someone you can match with, is it beneficial to always switch? Yeah, like, okay, if you have a free match, then use it. What if you... You've got like some openings. Yeah, so here we have like two things that have to close. Like two openings that need to close. How do we do this efficiently? We have to change two of them. I mean, there are only two types of ways of doing it, right? It doesn't matter which ones you change, so long as it's legal. Oh, it might matter though. This sounds like a really hard problem. Geothermal solve this in 13 minutes? 12 minutes? Dude, how are people getting this so fast? Let's check this cyan. Is this guy a cheater? Yeah, he's a cheater, but okay, green, who's popping off? This isn't really that important. Yeah, this guy seems legit. So this guy solves this problem. Seems to be a legit pupil. Solves this problem in like 30 minutes. Oh, maybe this is the delta to rating change. So he needs +7 to be expert. Double check to make sure we're doing this. Change any square to a round bracket. Oh, but not backwards. Wait. Oh, you can't do backwards. No, you can't. Ah, dude. Dude. I'm solving the wrong problem. Well, you gotta love that. That was fun. Okay. What do we say? We try solving the right problem now. Okay, you can change a square bracket to a round bracket, but not a round to a square. All right, let's actually start one sheet of paper with this right problem. Okay, so it's like solve the problem and maximize the number of matched square brackets. That's what we're asking, right? Yeah. If there's ever a mismatch, you have to turn them both to round. Okay. It's much easier. I think, anyway. At least from the amount of time it takes people to solve this correct problem, it seems much easier, because what I was trying to solve seems very difficult. Alright, so, okay, let's back up on the observations we've made before. It's kind of helpful. Yeah, so if everything were all round, then it would be somewhat easier, because we just have to make sure we don't run out of opening brackets from left to right or closing brackets from right to left. Those are the two requirements. You never run out. So it's just like two range minimum queries. And that would tell us how many things we have to flip. Okay, put that aside. What if we know how many things we have to flip? So we have to flip like two things. Which two things? So we have like close round, close round, close square, close square. But we're gonna have like close square, close round, close round, close square. So yeah, like two matching squares have to have like a matching round between them. Which is like not necessarily easy to calculate how to do. We still have like every A matches with a B, right? So you get like A, B, A, B, A, B. Yeah, you still kind of have that. Okay, so we just want to maximize the number of square brackets we use. Match with, I guess. So if we wanted to, we could do a DP. You know which things are on the stack? The DP sounds too big. So if we have something like this, then what? So, oh, I guess keep the direction when you can? Is that always true? Keep the direction when you can. If you have a working pair, keep their direction. Yeah, so this doesn't work. This is one too many closing. So we might as well switch this to forward. But why? If we have an open one of these and a closing one of these, that's not going to work. Yeah, if you ever keep a closing, I guess you can kind of just merge square brackets to the thing to the left of them. Like merge open brackets to the curly brace. Like you just push them out. You imagine pushing them out. You can have like subtrees that get deleted though. What? 0, 0. What am I solving? Am I solving the wrong problem again? Ah, dude. This costs $0. I am an idiot. I am a fool. Okay. Switching is free, so it's just how many square brackets can you match? Is it? That's all the problem is. Read the problem carefully, dude. This is... I spent probably more than half of contest solving 2 different problems that weren't in the set. I'm a fool. Well, it's good this isn't rated for me, right? Okay. How many square things can you match? That's the question. How many square things can you match? Yeah. How many square things can you match? Right? Surely. So when can you match, like, yeah, when can't you match them? Only if there's an even number of things between them, right? Or if there's an odd number between them, then they can't match. So you have a bunch of A's and a bunch of B's, and any A can match with any B. Yeah, so it's just the number of squares on A's and then on B's minus. Yeah. Yeah. Right? Okay. This is 0, dude. Oh my goodness. Okay. Oh boy. Oh boy. So we need array CS, I guess. That length plus 2. I changed my mind. This is not a code problem at all. Okay. And then we need the number of evens, the number of odds. Yeah, okay. So guaranteed each of these have even length. Okay. Is this right? This is E plus 1, S minus 1. Cool video stuff coming up. Okay, let's do this by hand. So 0, 1, 2. Yeah, how much? We'd better get this problem so we can get in 12 minutes. 0, 1, 2, 3, 4, 5. So if we want 1 to 4, then we have 0, 1, 2, 3, 4, 5, 6, 7. So we go to plus 1 and plus 2. Is this right? 62. Yeah. Okay. Sys out math.abs v2 minus v1. This is nonsense. This problem is nonsense. All right. Yeah, that looks fine. Nope. Sad contest. Very sad contest, ladies and gentlemen. For me taking it seriously, ugh. Oh well. Let's see if we got it first of all, I guess. Yeah. In all likelihood, we did. So let's use my notes as a proxy for what this contest was about. So yeah, I had 2 pages of notes, I guess 3 pages of notes on legit things, and then 4 pages of double-sided notes on problems that didn't exist in the contest. Yeah. So it was way more than half the contest was on problems that weren't in the set. Okay, well, anyway. That was confusing. We did it though, that's fine. Nice job, geothermal. Nice set solve. Very quick. Very quick. Yeah, I want to know how much of this, I guess I have the recording, so we'll see how much of this was on problems that didn't exist. Anyway, okay. Yeah, so there was my contest. Not a very good one, competitive-wise, because G was a nightmare. And then also I had a small bug on D. What was my issue on D? D2? Oh yeah. I had a cool trick, but it's just not right, unfortunately. Like, there's a way, if you know some element occurs the majority of the time, there's a cool way of finding it. I forget what the name is. There's some person invented this thing and it's named after him. But the idea is that you just keep a running total of like who is the most popular person. And then if you see someone who likes this value, you're like, okay, this is more likely to be the most common value. And if you see something else, you decrease the count for that value. And if the count ever goes negative, you set it to the new thing that set it to that. And the key observation is that if something occurs more than half the time, it will get added to at least half of the time, or decrease something else the other half of the time. So if something occurs more than half the time, that means at the end, after you've gone through the array, it will be the thing that's left over. If it occurs exactly half the time, though, that is not necessarily true. And I don't think there's an easy way of modifying this to get it to work. Although you can probably like special case it to still do it with like order 1 memory and order n time. But yeah, I guess you just don't need that because of the observation that n is 40. Okay. Let's talk about solutions here real quick, and then we can call it a day. All right, here we go. So yeah, this might be, I'll go over solutions somewhat briefly, and then I'll show my code for all the problems. So I guess when they load, let's look at code as a quick reminder for what this was. Yeah, problem A, you're given 3 different numbers for the problem, and you want to make each number the maximum. So if the number already is the maximum, you need it to win outright, like without a tie. I think that's something to do with elections was the flavor text. So to win outright, if it's the maximum, I just had a sorted copy of everything. So you've got a sorted version and the original version to keep track of the indices. So if it ties, like if you already are the maximum, then you do this case. If you're not the maximum, you just have to get to whatever the maximum is plus 1. Otherwise, if you tie with the second, or if you're the maximum and you tie with the second best thing, then you need one more move. Otherwise, you need no more moves if you're better than the second best thing. So that's the idea of problem A. Pretty simple. Okay, problem B. Yeah, for problem B, this was, you have to delete some digits to make it a multiple of 25. So any multiple of 25, you can just do this out by hand. It ends with 0, 0, 2, 5, 5, 0, or 7, 5. They guarantee it'll be possible, so we just want to brute force which 2 digits we delete, and then our runtime will be order like 81 per test case, because there are 18 digits, so it's 18 squared per test case, which is very small. So you just brute force the 2 digits you delete, or the 2 digits you keep for these last 2 digits that are going to be 0, 0, 25, 50, or 75. And once you know what those 2 digits are, all you have to do is delete everything after I except index j, assuming j comes after I. So you just do these 2 for loops, you delete everything after I except for index j, and then this is the number of things you delete, just the number of characters minus I minus 2. All right, yeah, and that's the idea of problem B. Okay, problem C. What was this? Codeforces. No. This isn't how things work today. Okay, good. Yeah, you've got the mice and the cat. So the observation here is that you have a bunch of cats, or you have a bunch of mice, and the mice are trying to reach the cat, and you have a bunch of positions here. And you've got like some mice maybe here and here. Every turn you get to, okay, so first of all you have a cat, which is moving this way. Every turn you get to move 1 mouse 1 space to the right. So the first observation is that the mice you end up saving, this is like the greedy principle here, are going to be some suffix of the mice that remain, or of the mice initially. In particular, let's say you would save this mouse, but you end up letting this one get eaten. Instead, every time you would move this one, you could instead move the one that's farther right, and that'll take fewer moves, so you'll have more moves left to potentially save other mice. And there's no benefit to taking this one here. So you're going to take some suffix of mice, and then also, obviously, each turn, you just, if you know which mice you're going to save, you just move the one that's in the most danger. And you do this repeatedly. So the total number of turns you have to get everything to the end is just like n minus 1. And the total number of moves you need to make is the number of moves to move everything into the last position. So you just sort the numbers from, I sorted them from smallest to biggest and went backwards, but you could also sort them from biggest to smallest. You can sort and then reverse it. And you just need to say, can you take this next thing? If you can, add 1 to your answer. Simple as that. All right. Awesome. Problem D. See, it sounds much easier when you have the solutions already written. You don't have to worry about coding it or bugs. But also, I guess that's what makes it fast, huh? Maybe I was like DDoSing Codeforces and they stopped returning my request. Maybe that was it. Yeah. So for D, this is much easier. We can solve it much faster than we would need to for this runtime, because it turns out this is like a pretty common idea. All we need for this to be the case is all of the differences between every element to be a multiple of some GCD. So if all of the differences are divisible by 7, let's say, that means we're going to turn everything into the smallest number. There's no use decreasing the smallest number, because if we do everything else, if we decrease it 1 fewer time, then we could just have it be whatever the smallest number was, right? So if we decrease everything by k, we might as well not decrease anything by k. So one thing isn't going to get decreased, that's going to be the smallest number. So now whatever that is stays constant. Everything else will get decreased to the smallest number, which means the difference between the smallest number and this has to be divisible by k. So we just take the GCD of all of the differences to the smallest thing and some other integer. And that's our answer. So yeah, D1, super clean. If you have your GCD function, which I think C++ gives you built in, then it's just a matter of doing this. You get the min, and then you take the GCD of all of these differences between the thing and the min. If it's 0, that means everything is the same. Okay, that's D1. D2 is a little bit more tricky because you have at least half of them. You can have half of them be the same. The rest don't have to be the same. They might be the same as each other. They might be different from each other. They might be the same as the first half. So obviously the answer is -1 if you have at least half of the elements be the same initially, which is not too hard to check. My implementation for that, sorry, I've got a little bit of, how did this pass? Oh, because I didn't submit this. Yeah, so this is what passed. So my implementation was I did a counting sort of everything. I use CS both for counting sort and cumulative sum, which I should probably fix. But I count the frequency of everything, and if anything occurs at least half of the time, I print -1 and continue. So that's what I'm doing there. Otherwise, you can notice that this GCD that you're interested in will be one of the factors of one of the differences between two numbers. So it's not necessarily some number in the minimum, because whatever the minimum number is might be in the group that you ignore, because you can ignore up to half the elements. But there's some number you don't ignore, and there's some other number which needs to be decreased to that. And then you're going to be taking the GCD of a bunch of things, but when you take the GCD of something and what it used to be, basically you're just taking what it used to be and then now picking one of the factors of that. When you take the GCD of something and what it used to be, like, you just pick a factor, and that's what you're left with. You can't ever choose something that isn't a factor. So since you're taking a factor of something and what matters is like some difference, you're going to have some difference and then some factor of that difference. That was a little hand wavy, but I think it's much easier than understanding the math. It's just understanding what GCD is. So yeah, instead of, like, you can do this in about 10 to the 8 runtime, which might run in time. It'll be close. TLE's in Java, probably. I don't think you can get it to pass in Java. Maybe in C++ though. But you can also make the observation that you don't need to try all these Ks. You can only try a few Ks, and then that'll be good enough. In particular, you just take every difference and then try every factor of every difference. And this is, I have some duplicates here, but this is good enough. So to check if something works, you just see you're going to pick half of the element, like you have this K, and you're going to decrease everything by K, which means the value of some element under mod of K will be constant, because you always subtract K, so its value mod K will stay the same. So you want to see, is there any value mod K that has over half of the elements? That's what you're checking here. And yeah, you just do that pretty simply. So I just mod everything by K and then sort the elements. I know they're all positive, which is why this works. Then I sort the elements, and then I count adjacent things here, so I don't have to use a hash map in case it was close on time, but it probably wouldn't be close on time, so this probably doesn't matter. Okay, yeah, that's D2. 3 more problems. We got E, F, and G, and should be nice and quick here. So E, gardener in the tree. So this is a very good problem if you are not familiar with doing, what are the things called? Topological sorts, because this is a great use case of them. It tripped me up in the beginning. I thought it was a BFS, but it's not. It's a top sort. So something becomes a leaf when all of its children, all of the things adjacent to it, except for one, get removed. Which means we can just store for every node. Either if it is a leaf, we're going to put it in some queue. And if it isn't a leaf, then we'll say, okay, remember what your out degree is. Remember how many neighbors you have. Or alternatively, what I did, because I thought it was easier to implement, is remember how many neighbors you have deleted, and then you also know how many neighbors you had initially. So if you subtract those two, you'll get how many you have that are undeleted. And each time you remove a node, you can just see, okay, well, look through all of its edges. For any of those things that are undeleted, there will only be one of them, at most. For any of the things that are undeleted, subtract 1 from the number of current out degrees it has, and if now we've made this thing become a leaf, then add it to the next layer of things that get deleted. So we can just see, like we can just imagine taking n steps here and seeing, okay, how many nodes end up getting deleted. On the first step, on the second step, on the third step. So we know how many deleted at each step, which means we can answer this query of k really easily. It's just the number of things that are deleted on a step less than or equal to k. I slightly overcomplicated my implementation there, but it's not too bad. So yeah, here's the idea. Build the tree. I call this a BFS, but really this is the top sort. So first I go through every, yeah, this is slightly misnamed because my first solution was wrong. My first submit was incorrect. Yeah, I guess I'll draw a good counterexample for why it isn't a BFS. So here is the case that I had on paper. Something that looks like this. So all of these things get deleted on turn, I guess we'll say turn 1. And then these things get deleted on turn 2. Now if you did a BFS, this is distance 2 from a leaf. But it doesn't get deleted on turn 2, it gets deleted on turn 3. Because it has 2 neighbors that get deleted on turn 2. So it isn't deleted until turn 3. So if you have this tree and then k equals 2, if you do 2 steps, you'll have 1 node remaining, not 0. So yeah, that's a break case for the BFS. Good case to try. Yeah, so then this is the BFS, which is actually a top sort. I misnamed it. But yeah, just continue looking in this queue. If this thing, so now we have this node that we're processing here. We're going to iterate through all of its edges, and if the thing this edge goes to has already been removed, then we skip it. Otherwise, we add 1 to the number of deleted edges this thing has, and now we check if it's a leaf. So if its size minus the number of things we deleted is either 1 or 0, that means we've made it a leaf. So say, okay, it's getting added in this layer, and then add it to the BFS. And then after this, I do a cumulative sum to see how many things are deleted at each layer or earlier. Okay, cool. That's the idea for problem E. Nice and easy. Nice solid. Okay, red, black number. Another very good instructional problem. Definitely solve this if you haven't and don't know how. This is a very, very good problem to know how to do. It's a pretty basic digit descent DP, but this is a very standard idea. So this shows up all the time. You got to be familiar with this. So basically the idea is, or the problem is, you have some really long digit, or really long string of up to 40 digits. But in other problems, these can get bigger. They get up to like 10 to the 5th digits sometimes. It'd need to be an easier version of the problem to do it with that many digits, but that's the idea. It happens all the time. So you have some very, very, very big number, and you have to do something with it, but the thing you're doing with is like, it happens mod 10 or mod 40 or something, mod something small. In this case, you're doing 2 things, both happen mod 40. So you need the remainder mod 40 of some of the digits to be 0 and mod 40 of some of the other digits to be 0. So basically what we're going to do is pick some set of digits. These digits have to have a value mod 40 that's equal to 0. The digits we don't pick have to have a value mod 40 that's also equal to 0. And we want to pick about half of the digits. So instead, if we just brute force the number of digits we're going to pick, then we can try all of those possibilities and pick whichever one is best. So in particular, you should probably see this coming from quite a ways away. The DP status, or DP state, is which digit you're on, what the remainder mod R is, and what the remainder mod B is, and then also how many reds to pick you have left. So yeah, this is the DP state. Let's talk about the transition real quick. So the base cases are if you processed all the digits, if one of your remainders doesn't work, then it's impossible. So I return 0 for impossible and 1 for possible. So yeah, if your remainders don't work, it's impossible. If you picked the wrong number of reds, then it's impossible. If you've picked too many reds, then it's also impossible. Otherwise, we have to try the 2 possibilities. So either this digit will be red or it'll be black. In either case, we go to the next digit. So digit becomes digit plus 1. The red total, if we paint this one black, paint it black. If we pin it black, then the red total will stay the same. But if we pin it red, then the previous thing gets shifted over by 1. So we multiply the previous value by 10. Then we add the value that we're about to place. We add this digit. And then we have to mod it by A. And then the black total stays the same. Otherwise, we do the same thing with black, but mod B. And if we pick a red, then we want to pick 1 fewer red going forward. So that's the idea for this. Hopefully that made sense. Okay, cool. Yeah, and then we return the answer at the end. So this will tell us whether or not it's possible. Then we also need to do a build back. So build backs are also another good thing to learn. Oops, that was important. So the build back for a DP will be, you just copy and paste the same DP, but now you only go down this DP tree once. So you see if this is the right answer, then do this thing. Like print take a red, and then continue building back this answer. If this was the wrong answer, that means we took this other transition here to get our optimal answer. So then call the same thing, like printed B, and then call the same thing, the same DP transition, but here we're in the build back rather than in the DP, and we continue printing it. So we keep going down this tree, or this list of states, and then we print the things we take. So the DP is to calculate the answer. We run this ahead of time to figure out the best answer, and then we run the build back in order to print it. And this will like look at the possibilities, be like, okay, which one's the right one, and then take that one, and then print the answer, and then keep going down. So yeah, digit descent DPs are a really common thing. Build backs are another really common thing. Both of those are things that you should know if you're going to be doing Div 1 problems seriously. All right, and then this is an idea that I've seen a million times, but I couldn't read the problem, which is you know, an important part of doing programming contests, being able to read, because the statements are in English and you don't have people explaining them to you like this, right? So you have to be able to read the problem, and I guess if you notice that it's way too hard, then you should try rereading the problem like twice. So yeah, the understanding this problem is probably the hardest part of it. First, this sentence is just very important, and second, this sentence is very important. So yeah, if you change either of these sentences, the problem gets much harder. You've got 2 types of brackets. You've got these rounded brackets and square brackets. You can change whether it's an open or a close for free. For free, it's a move that you get for free, but you can change whether it's a square to a round at a cost of 1. So yeah, the question is, you want to minimize the number of times you change a square bracket to round. In other words, you want to maximize the number of square brackets you match, where doing this part is free. So the key observation here is that you have like 2 types of positions. You have even indices and odd indices, and your open brackets will always be, doesn't matter how you do it, but your open brackets will always be on the even indices. Nope, JK, this is, or like, okay, sorry, let's try this again. So here's a position, right? This position is a bottom level position, which means it will match with the top level position. So any way that you do this, you are going to have this match with something on the top, right? Let's say you want these 2 to match. This is obviously impossible because you have one thing here. So either this is an open or it's a close. Either way, it's not going to have a matching pair. Yeah, that's the idea. If you give me some set of things that need to match, right? If you say like you've got this one, this one, this one, and this one, now you've picked 4 things, we can match them like this. Nope, JK, we can match them like this. First and last, and then these 2. And then these ones will be left out matching as well. So yeah, it'll always end up working as long as you follow this rule. Now, yeah, you need to pick the same number of things on the top as on the bottom to be square. That's the idea. So now the question is, if you're given some even length range, you just want to see how many square things are on the top and how many square things are on the bottom, right? How many square things are at even indices, how many are at odd indices. And you can do this just by keeping 2 cumulative sums, but your cumulative sums will count by 2 rather than by 1. And that's basically the idea. You just do it on paper and then like see, okay, if my cumulative sums count by 2, what indices do I need to subtract to make this work? You just do like a mildly decent sized case by hand, and they're like, okay, yeah, it's this minus this. There you go. I'll show you the code for it real quick. Yeah, it's really, really clean. So you got this cumulative something. Usually this is n plus 1, but I just make it n plus 2. And you add 1 if it's a square bracket. Then you build this cumulative sum by the thing 2 before it. And this is how to check how many are on even indices and odd indices. I might have the even odd part mixed up there, but one parity and the other parity. And then whichever has more, you'll have to decrease that to have the same number as the other one. So it's just the absolute value of the difference. That's your answer. All right, that is the idea to problem G, and in fact to all of the problems in this set. Hopefully you enjoyed the contest. And yeah, reading G was the hardest part of the set. Oh my goodness, yeah, it was kind of annoying. I didn't think any of the problems were too hard, but I almost didn't solve it, right? So you got to be careful. Keep your weight on your toes, because you never know when you're going to be solving something that doesn't exist. I don't know. It's interesting. I wonder if there is a solution to the versions of that problem that I didn't solve. I don't know. I'm not sure. Okay, anyway, thank you for watching. Have a great day, and I'll see you in the next contest. Goodbye.